Now we'll start with the concept of law of conservation of angular momentum. As we know, for a rotating rigid body, we write angular momentum is given as I omega. For a rotating rigid body which is rotating with an angular speed omega, whose moment of inertia is I, you can write its angular momentum to be given by I omega. Let's differentiate it with respect to time. If we differentiate with respect to time, we get dl by dt is equals to I d omega by dt, which can be written as I alpha, as d omega by dt is the angular acceleration of body, which can be written as I alpha, which we know the net torque acting on the body, or net summation of all the torques acting on the body can be written as product of moment of inertia and angular acceleration. So here we can write net torque acting on a body can be written as dl by dt also. So here we can see this is just an angular counterpart of Newton's second law, where in translational motion we have studied rate of change of linear momentum is the force applied. We already studied F is equals to dp by dt. So it is just the angular counterpart or rotational analog of this particular analysis, which we can state at Newton's second law for rotational motion, which can be written in words like rate of change of angular momentum of a rotating body is equal to net torque acting on it. This is the Newton's second law in rotational motion. As in translational motion, it is rate of change of linear momentum of a moving body is equal to net force acting on it. In sequence, we can say if for a system of bodies, even we can talk about a single body, net external torque acting on a system is equal to 0. This implies dl by dt is also equal to 0. For a given body, if rate of change of angular momentum is 0, that implies we can say that angular momentum will remain constant with time. We can also have a relation that dl by dt is 0 implies L can be maximum or minimum, but here we are talking about a continuous duration. So there can be only one case that if L is a constant, continuously we can state that dl by dt will be 0. So we can say in absence of external torque on a system, total angular momentum of the system will remain conserved. Here total angular momentum of the system means angular momentum of all the objects which are there in the system, and if there is a single body or two bodies, sum of the vector angular momentum of all the objects of the system will remain conserved if no external torque is acting on the system. This we can simply state as law of conservation of angular momentum. Just to understand the concept of conservation of momentum, let's have an example. Say we are having a disk which is of radius r and mass m, which is rotating about a given axis of rotation. So its mass is m and the radius of this disk is r. Say it is rotating at an angular speed omega naught in an anti-clockwise manner. In this situation, say we drop a small object of mass m onto the disk, and due to friction, say it will stick onto the disk and will start rotating along with the disk. So in this situation, as the disk was moving in anti-clockwise manner, the friction will act on the disk in opposite direction and the same friction will act on the object in forward direction or opposite to the friction on disk. Now this friction will accelerate the object to move it along the motion of disk and the opposite force will be acting in backward direction. Now as the friction here is the internal force, we can state net torque acting on the disk due to friction is 0 or it is the internal force, so no net torque is acting. If we talk about axis of rotation, this might exert some external force, but as it is acting on the center of the disk, no torque will be applied due to the external force by the axis of rotation. So here we can state as no external torque is present, here L of the system will remain conserved. If we talk about the initial angular momentum that was only due to the disk, that can be written as I omega, which is half mr square into omega naught, because the moment of inertia of a disk about central axis is half mr square. Its angular speed was omega naught, so angular momentum initially was half mr square omega naught, which must be equal to the final angular momentum after addition of the mass. Say its angular speed after addition changes to omega final. So the moment of inertia we can write as half mr square plus small mr square, because for a point mass moving in a circle of radius r, its moment of inertia can be written as small m into r square. This multiplied by omega f. So here directly you can see the final angular speed can be given as, here r square we can cancel out. This will be given by m omega naught by m plus 2m. So this will be the result of final angular speed, which we have very easily calculated by conserving angular momentum, and we were able to conserve angular momentum because no external torque was acting on the system.